Have you ever wondered how something as simple as a picture of dots and lines could help us predict how a virus spreads, or how it could power a search engine? Well, today we're going to dive into this incredible hidden connection between pictures and numbers, a journey that turns simple drawings into some of the most powerful tools we have. And believe it or not, it all starts with a very old puzzle. Right, let's get into it. Our story kicks off way back in the 18th century in this beautiful Prussian city called Königsberg. And it was pretty famous for its unique layout of islands and, you guessed it, bridges. So the city had these 7 bridges that connected everything up. And for years, the locals had this little brain teaser they'd chew on. Could a person actually plan a walk through the city where they cross every single bridge but only cross each one once? No matter who tried, nobody could figure out a route. It seemed impossible. And it turns out they were right. In 1736, this absolutely brilliant mathematician, Leonhard Euler, proved it couldn't be done. But what's really amazing is how he did it. He basically ignored the map, stripped the problem down to its bare essentials. He turned the land masses into simple dots, what we call vertices, and the bridges into lines or edges. And just by doing that, he accidentally invented what we now call a graph, and kicked off the entire field of graph theory. So what is a graph really? And more importantly, how do we take this simple, intuitive drawing and turn it into something a computer can actually work with? Well, that's where the magic of matrices really comes into play. At its heart, a graph is just that, a bunch of vertices, the dots, and the edges that connect them, the lines. That's it. But these simple structures are the building blocks for basically all networks, from your friends on social media to the entire global flight network. And this right here shows the key step we need to take. On the left, you've got the visual graph. Our brains get this instantly. But computers, they don't really see pictures like we do. They process numbers. So to let a computer analyze this network, we have to translate this visual map into a nice, structured table of data. And that table has a name, an adjacency matrix. Just think of it like a connection map, or maybe a flight schedule. It's a grid where every row and every column stands for one of our dots, one of our vertices. If you see a 1 where row I and column J meet, it means there's a direct connection, a direct flight between them. If you see a 0, nope, no direct connection. So here's the bottom line. We now have 2 completely different ways to describe the exact same network. The visual graph is awesome for us humans, for our intuition. But the adjacency matrix, that's a precise numerical object that computers can perform all sorts of calculations on. And this simple translation unlocks some absolutely incredible abilities. Okay, so we've got our graph all neatly packed away inside a matrix. Big deal, right? What can it actually do? Well, this is where a really simple math operation reveals this hidden, almost magical property about the entire network. Let's ask a really specific question. Imagine our graph represents cities and flights. How could we figure out the exact number of different routes between 2 cities that are, say, precisely 3 flights long? Not 2, not 4, exactly 3. Trying to count that by hand would be an absolute nightmare. But the answer is just unbelievably elegant. This is one of the core theorems of graph theory, and it says that if you take your adjacency matrix, A, and you just raise it to the power of k, the new matrix you get has the answer. The number in row I, column J, is the exact number of walks of length k from vertex I to vertex J. It's incredible. Now there's a really important word here, walk. In graph theory, a walk is not the same as a path. A walk is just a series of steps. You are totally allowed to go back on yourself, to reuse edges and revisit vertices. You could go from city A to B, then back to A, and then over to C. That counts as a 3-step walk. This is a super crucial distinction. All right, theory is one thing, but let's actually see this in action with a real example. It really is one of those things you have to see to believe. Here's the graph we're going to play with. We've got 6 vertices, V1 through V6, and a bunch of connections between them. Now, we're going to use our new matrix superpower to figure some things out. First things first, we build the adjacency matrix, which we'll call A. This matrix is just a snapshot of all the direct connections. You could say all the possible walks that are exactly 1 step long. You can see a 1 anywhere 2 vertices share an edge. Okay, now for the main event. Here's our challenge. How many different ways can we get from vertex 6 all the way to vertex 4 in exactly 3 steps? And remember, we can backtrack and go in circles if we want. So to solve this, we don't have to trace a single thing. All we have to do is calculate a cubed. A times A times A. And this is the beautiful part. We just look at the resulting matrix. We find the entry in row V6, column V4, and bam, the answer is 8. There are exactly 8 different walks of length 3 from V6 to V4. And we can actually prove it. Let's just trace a couple of these 8 walks on the graph itself. So one way is to go V6 to V2, then V2 to V1, and then V1 to V4. That's 3 steps. Here's another fun one. V6 to V4, then back to V6, then back to V4 again. Because we're allowed to reuse edges in a walk, that totally counts. The matrix did all of that complicated counting for us in one single calculation. That's the magic. So as you can probably tell, this is way more than just a clever math trick. This is a really fundamental tool for understanding the incredibly complex networks that basically run our world. I mean, think about it. You can use this exact same principle to model how a disease might spread through a population in 3 stages. It can help analyze social media to see how information flows and who the key influencers are. It's at the core of optimizing shipping routes, designing cell phone networks, and it even helps power the algorithms that rank web pages when you do a search. Which really leaves us with a pretty fascinating question, doesn't it? We started with a simple puzzle about some bridges and ended up with a tool that helps run the modern world. So if just raising a matrix to a power can so perfectly count the pathways in a network, what other secrets about our deeply interconnected world are just sitting there, waiting to be unlocked by the elegant power of matrices? Thanks for joining me.